Hi, this is lecture 20 of M2 So, in last session we have seen some result about differentiable function. A function u to r is differentiable if some condition is satisfied. Now we have said one result that says, suppose f is a f is this one that I am starting with. Suppose f is such that if a point a belongs to u is a point of local minimum or maximum for this function f, then we have seen f dash of a is 0. This can be minimum or maximum, minimum point or maximum point, local minimum, local maximum. Then we have seen f dash of a is 0. Now this suggests maybe we should ask a different question. What is it? Suppose we have a function f from u to r and it is differentiable. Suppose I know some result, some condition about this derivative f dash u to r, can I say anything about this function given some property of the f dash? Can I say anything about property of f? Here we are going in this direction. Given a function f that is differentiable, suppose there is a point a belongs to u, that is a point of local minimum or maximum, that means is property of this function f, right? Then we have said something about f dash at that point. So here we are trying to do the other way. We have a function f from u to r, we know it is differentiable, so f dash makes sense. Now we are saying suppose we put some condition on f dash, can I say anything about this function f? That is what we are trying to understand. So now the question is, what conditions can I put? This is a function, so I can ask some properties. I know some properties of function. What is it? I know what is a bounded function, I know what is a continuous function, and monotone function, increasing, decreasing, like that way I know. So we'll try to ask one by one. So firstly, if is differentiable and f dash is so let us ask f dash is bounded. So before we try to proceed in that way, we should at least know that what is given a function f, is it possible that f is bounded but f dash is not bounded? Would it be possible? Think about it. I am not going to say anything more here. It is interesting, so I am not saying that. Check for yourself. Given a function f, even if it is bounded, can I think of an example of bounded function f that is differentiable, but f dash is not bounded? So asking for f dash to be bounded may not be that interesting. So that is not a good idea. Now if it is differentiable, see, forget about anything else. Even though if it is differentible, f dash, see this continuity, I said it is differentiable, so it has to be continuous. This continuity itself is not, one cannot say anything about continuity of f dash. So in this process, continuity itself is lost. So boundedness, it is not very clear whether it will transfer to the derivative or not. Continuity need not transfer to the derivative. There are functions f from u to r that are differentiable, so continuous of course, but the derivative is not continuous. So this kind of example you should come up with some examples like that. So now we have two exercises. So think of differentiable functions that are bounded but their derivative is not bounded. Think of differentiable functions that are continuous but the derivative is not continuous. This kind of things, it's useful in future, for later purpose, to have this kind of examples. Now why did we do this? We were trying to see whether imposing a condition on f dash say anything about the function f. So imposing bounded condition is already too much, because there are many interesting examples of functions. I am not finishing the sentence, but there may be functions that are bounded but the derivative is not bounded, that kind of things. So now what is the next best thing that we can impose on the derivative f dash? What is the next best thing? of course we have something called order on R. So one can ask either f dash A is a positive for every A belongs to U, or f dash A is negative for every A belongs to U. This kind of things we can ask. So we could not say anything about this bounded or continuity part, but at least this may be fair place to start with. So let us start at some point. So let us take a differentiable function f and assume that f dash has this property, f dash A is non-negative for every A belongs to A belongs to U. Then can we say anything about this function f? So as I said, for bounded things, I left as an exercise that there are interesting functions f from U to R that are differentiable, bounded, but the derivative is not bounded. So maybe the starting point to proceed from here is that do we at least have some examples of differentiable functions whose derivative has this property, that we will check now. F from U to R is differentiable such that f dash of A is non-negative for every A belongs to U. So now we should look for differentiable functions with this property. It may be it's not very clear how to even guess. So what we do is we will take some non-negative function and then see whether we can come with a function f such that its derivative is the non-negative function. So one non-negative function that I know is just square function, fx is equal to x square for every x belongs to R or x belongs to U, whatever it is. This is the first non-negative function that I can think of, or x power 4, x power 6, or x power x to the power of even number, some even number. Now do I know some function f? Maybe this is not f, this is a g. Do I know some function f whose derivative is x square? Yes, we know that fx is equal to x cube of then f dash is what? F dash is 3x square, right? But this also non-negative, right? The 3 is positive, x square is non-negative function, so f dash x is non-negative function. So x cube is a nice candidate. So we have a function f from U to R that is defined as the cube function fx is equal to x cube, and the derivative f dash x is a 3x square. It is non-negative for every element x belongs to U. Now we are looking at some property of f. So you might have seen a graph of this function. So just looking at the graph, the first thing that you can recognize is that it is increasing. I mean, even without drawing a graph, you can still conclude that it is increasing function. How do we know that? So we should check if x is less than y, then we should check if x is less than fy. What is fx? It is x cube, fy is y cube. So we are checking whether this is the case or not. But that means what? We should check x cube minus y cube is less than or equal to 0, whatever it is. X is less than or equal to y. Now this is what? A cube minus b cube is a minus b times a square plus xy plus y square. Is it true? That is what you are trying to see. X is less than or equal to y. So this thing is less than or equal to 0, that is fine. But we should also know that this is a positive, only then this product will be less than or equal to 0. So now we are checking for x square plus xy plus y square. Is it always positive for every x comma y in an appropriate domain U? Xy belongs to U. Now for every x and y, this is positive, but this may be negative. So just by looking at that, it is not very clear whether this whole thing is positive or not. So what we do is we will try to do some small computations with this, then conclude that it is and then see what happens to that. Instead of considering this, let us consider a multiple of that, 2 times x square plus xy plus y square. What is this? 2x square, 2y square plus 2xy. Now I think you know what I am going to do. X square, not 2, x square plus y square plus 2xy means something for you. What is it? X plus y whole square. Now we took only 1x square, 1 y square here, so there is one remaining. So this is x square plus y square. So what we know is the following: for any x comma y in U in R, this is positive because it is square, it is positive square, it is a positive square. So this sum is a positive element, non-negative element. So 2 times something is non-negative, 2 is non-negative, so this has to be non-negative. So this says x square plus xy plus y square is greater than or equal to 0 for every x comma y in U. So now what do we have? We have this fx is less than or equal to fy for every x comma y in U. So now what did we conclude? Now what did we observe? We have a function f x equals to x cube. The derivative is non-negative. Then we have seen that this function is increasing. See, it looks like, I mean, we want to say that if a function f is if a function f is such that f dash is non-negative, then f is increasing. We want to say something like that. But just with one example, it's not very clear whether we can make that kind of claim. I mean, proof is a secondary thing. First thing, we only have one example, and it's not very clear whether non-negativity of this is playing any role in increasing property of this function. Let us try with some example, some differentiable function f, so that the derivative is not always non-negative. I mean a function f whose derivative, it can take both positive and negative values. Let us check with that kind of example and then see what can we say about this function f. So now what we are doing is, we are looking at a function f u to r such that f dash of x can take both positive and negative values. So one function that we know that takes always non-negative value is x square, one function that takes always non-positive value is minus x square, so that it's always now one function that takes both positive and negative value is what? I mean, whenever something is negative it takes negative, whenever something is positive it takes positive. So one example is fx is equal to x. So here f dash is what we are considering, f dash x is equal to x for every x belongs to U. So now we are looking for a function f whose derivative is x. Many of you can guess what f could be. So fx is equal to x square. X square is one function whose derivative, what is f dash x? That is 2x. We wanted to have x here, but we got 2x, that is still fine. This function also takes both negative and positive value if U has both positive and negative value. So we are assuming that. So let us study this function fx is equal to x square, f dash x is 2x, it takes both negative and positive values. Then does it in any sense affect the increasing nature of this? We know that x square is the function, this function, I'm not good at drawing something, assume this is 0. So this function is not increasing, see it's decreasing in this portion and increasing here. So it looks like, maybe last time I said for x cube, I said you don't really need to draw the graph to conclude that f is increasing. So let us try to write down some details here also. So let us check this without looking at the graph. So fx less than fy, this is what we are supposed to check, if x is less than y. Is this the case? This is a question mark. Now what is xy? Fx is x square, fy is y square. So x square minus y square is less than 0, x minus y times x plus y is less than 0, x is less than y, this implies what? This is negative. So only when this is positive one can conclude that this is true. But given two elements x and y, it's not very clear for the arbitrary element x and y x plus y should be positive. One can take x is equal to minus 1, y is equal to minus 1, then x plus y is minus 2, it is negative, so this is not the case. Or it can happen that maybe less than is not correct, greater than may be correct. We don't really know that, right? So now what? For this to hold, what we want is x plus y should be negative always, but again we are looking for elements x and y belongs to U such that x plus y is a positive. Can we think of some example? 2 plus 3 is 5 is positive. So it is not consistent that there may be elements U elements in U such that x plus y can be positive or x plus y can be negative. So in that case we cannot really say that f is increasing or decreasing, that is not very clear. That is not true also, that if I take some if I take U as this, in some portion it is decreasing, in some portion it is increasing, so we cannot really say anything about that. So maybe the non-negativity of derivative might play some role, might be playing some role in increasing nature of the function. This is our guess. Let us check that. So f from U to R differentiable, I am starting with the differentiability, and f dash of A is non-negative for every A belongs to U. Now we are checking whether f is increasing or decreasing, that is what we are checking. So let us fix 2 points x comma y in U. Then what? We are trying to relate fx with fy. This is what we are trying to say, less than, greater than something. Think of some result that relates between these elements and some derivative of some element. I think you are already guessing what I am going to do now. Given 2 elements x and y in U, there is a point A in between x and y such that fx minus fy by x minus y is equal to f dash of A. What is this is called? Some mean value theorem, right? Now what? See, we are assuming x is not equal to y, so I can of course write down x minus y here. Now what? F dash A is non-negative, so this is non-negative. So this fraction is non-negative. I assumed that x is less than y. I didn't assume, yeah, I have done here. X is less than y. So what? This thing is negative. So unless we have already we know that this is non-negative. For this thing to be non-negative, this thing should be negative. Fx minus fy should be less than or equal to 0. These two will be less than or equal to 0. So the corresponding so this quotient will be non-negative. So what is this? This is same thing as saying fx is less than or equal to fy. So this says what? Now we have a result that says, suppose we have a differential function such that its derivative f dash of A is non-negative for every A belongs to U, then f has to be increasing. F has to be increasing, that is all. Now let us try the other way. Suppose I know that f from U to R is increasing. Suppose it is increasing. Then do I know that f dash A is non-negative for every A belongs to U? Is it the case? That is what we are trying to see. Now let us fix some element A belongs to U and let us check f dash of A. What is the definition? Limit h goes to 0 f of A plus h minus f of A by h. Now we have what? F is increasing. Suppose h is negative. Let us take some element h is negative. Then what? A plus h is less than A, right? H is negative, so I am just adding A on both sides, so that gives me A plus h is less than A. This says what? Because f is increasing, f of A plus h is less than f of A. This is same thing as saying f of A plus h minus f of A is negative, and we already know that h is negative. So this says this fraction is positive. Similarly, suppose h is positive, then what? A plus h is greater than a, f of a plus h is greater than f of a. So that says f of a plus h minus f of a by h is greater than 0. So in both cases, for h negative and h positive, this thing is it's taking only positive values. Then this limit, there is some important point here. Even though one can have a function f, the whole thing that I am treating as a single function, one can have a function f that takes only positive values, not at this point but to the left and right of that point. But when we reach when we take the corresponding limit, this limit can be 0. It is possible. So the best that we can ask is, it is because it is positive, the best we can ask is, we can ask that it is greater than or equal to 0. So we do not know whether f dash a is strictly positive, we do not know that. What we know is f dash a is greater than or equal to 0. This is what we know. Okay, let us look at the following example. Suppose something like this. So f is taking a positive value to the left side of this, to the right side of that, but f of this element is 0. So in that sense, one can have for this function that to the when h is negative, when h is positive, at both places this function may take a positive value, but when we try to take the limit, it can take 0. That possibility is there. So we are not saying f dash is positive, we are only saying f dash is non-negative. So now what do we have? F from u to r is increasing. This implies f dash of a is non-negative for every a belongs to u. This is what we have. Now, do we have any example of a function that is increasing and f dash a is 0? Is it possible? We do not have to look very far. We have a function, just now I said that f x equal to x cube is an increasing function. F dash x is 3x square. If you consider this function in R or any interval that contains 0, f dash x is such that f dash of 0 is 0. So there is a point A inside this domain such that f dash of that is 0. So even though f is increasing, f dash of that, even though f is increasing, the derivative need not be always positive, it can take 0 value, but it is always non-negative. That's what we can confirm. Now as an exercise, I am leaving to you to check what conditions should I put on either f dash or f such that there is one correspondence, that increasing function. Okay, suppose if it is increasing function, we cannot really say f dash is positive. What extra condition should we put on f so that f dash is always positive? Maybe I will add something in the lecture notes, but before checking that, try by yourself. What conditions can I put on this function f so that increasing implies f dash is positive? So this is one question. One can just go back to the place where we have started. I am starting at what? F is differentiable and f dash is non-negative. One can start with non-positive. One can start here less than or equal to symbol. Then one can conclude that if f is differentiable and f dash is a non-positive, then f has to be decreasing. Then similarly one can also prove, suppose f is decreasing, then f dash can be, it can take 0 value, but it's always non-positive. Okay. Now, so till now what we have seen is the following: starting with a function f, if only it is differentiable, and the derivative and increasing decreasing are seems to be in some nice correspondence. That if f is increasing, then f dash should always be non-negative. If it is decreasing, then f dash should always be non-positive, and strict increasing is not really saying anything about the strict positive or negative thing. And I asked you to check for yourself. You can take help from the internet or any other textbook. Try to understand what extra condition should I put on the function f, so that increasing is corresponding to the derivative being positive, decreasing corresponding to derivative being negative, strictly negative. Now let us increase the complexity slightly by looking at functions that are both increasing and decreasing. Till now we have seen only one property at a time. Let us now consider the functions f that are both increasing and decreasing. The first kind of functions that we can think of, that I can think of, that are both positive and negative, are the so called convex or concave functions. Right, this is the first set of examples that we might have learned. These functions are something is of this form, something is of this form. So now we will try to focus our attention on functions that are differentiable and convex. Can we say anything about the corresponding derivative? So let us first check. Let us recall the definition. You might already know what is a convex function, concave function, but I'll write down the definition. So suppose f is a function from u to r. F is said to be convex if given 2 points x1 and x2 in u, and for any point in between x1 and x2, any point in between x1 and x2 is of the form tx1 plus 1 minus 3 times x2. This is how any point in between x1 and x2 look like. For any point, the image f of that is related to fx1 and fx2 in the same order. If it is less than or equal to, then we will call f to be convex function. We will call f to be convex function. If it is greater than or equal to, then we call f to be concave function. So before we proceed further, check for yourself. You might have learnt other definition of convex function. Check for yourself whether the definition that you know is equivalent to this definition or not. I am saying again, convex means it is less than or equal to, concave means it is greater than or equal to. And now let us check the derivative of this kind of functions. F dash from u to r, this is f dash. If f is increasing, then we know f dash of a is non-negative. If f is decreasing, then we know f dash of a is a non-positive. Then can we say any such result for this kind of functions? For a convex function, let us start with convex function. Can I say anything about f dash? That is what we are trying to, that is the first thing that we are trying to see. Is it always non-negative? Is it always non-positive? Is there a point? Do you know that? Do you know examples of convex function that takes both positive and negative values? Is it something like that? In this session only, I have mentioned some example of convex function. Check for yourself if you have not observed that, of a convex function whose derivative takes both positive and negative values. I have mentioned that already. I am not revealing that. Go back to the video and then find it for yourself. Okay. Before we proceed to this derivative, it's useful to know an alternative description of a convex function. See, we are trying to look at the derivative. How does it look like? One form of that is what? Fx minus fa by x minus a, limit x goes to a. this is f dash of a. So this is how it looks like. Now there is an alternative description for concave function or convex function. So this says what? For any element x in between x1 and x2, something happens. That is what we are saying. So let us rewrite this. Again it is an exercise. So this is something as saying, for any x belongs to x1 and x2, we have something to say about fx. For sure it is less than or equal to. So we are trying to write down it as a general element x, and we have to make some change here also. So what is the change? So this is less than or equal to fx1 plus fx2 minus fx1 by x2 minus x1 times x minus x1. This is true for any x belongs to x1 x2. It is not very difficult to check. See, at least this may be standard that you might have seen before, this may be new, but I am saying these are not very different. What I am saying here is, here we are denoting the element using the help of some variable t, but here we are not doing that, we are taking any arbitrary element x belongs to x1 and x2. Then we are saying this condition is now turning into this condition, that is all. Again for concave we will have something like this, and there is something called strict convex, which means this equal to symbol is not there, and similarly these are equivalent conditions. Suppose for x1 and x2 and for every x belongs to this, suppose we have this, then f is convex in the previous sense. So this can be seen as a equivalent description of convex function. Okay, now we are trying to see that for convex function, what can you say about the corresponding derivative? That is what we are trying to see. So f from u to x, u to r is convex. Now we are trying to look at the corresponding derivative. See, as I said, it can take both positive and negative values. Look at the function x square, it is taking both positive and negative values. But what can we say about the so it does not make sense to talk about the derivative being non-negative or non-positive. The next best thing that we can do is the following: we take two elements, let us check how does f dash of those two elements are related. So x1 and x2 belongs to u, then we are looking for the relation between f dash of x1 and f dash of x2. This is what we are trying to do. For single element, we cannot really say it is positive or negative, that is out of question, because for x square it is convex. Is it convex or concave? Check for yourself. For fx is equal to x square, we have f dash is equal to 2x. So this takes both positive and negative values. So it does not really make sense to talk about f dash of a being non-negative or non-positive always. So the next best thing is, okay, let us take two elements x1 and x2 in u, then can we say anything about the relation between f dash x1 and f dash of x2? This is what we are trying to see. Now at least we should write down what is the definition of convex function here. So for x1 and x2 in u, f being convex means what? For every x between x1 and x2 we have this property. Let us write down that at least fx less than or equal to f of x1 plus fx2 minus fx1 by x2 minus x1 times x minus x1. So let us try to do some very obvious computations. So this is something as saying fx minus fx1 is less than or equal to fx2 minus fx1 by x2 minus x1 times x minus x1. Again one more simplification. This I am pushing here. Can I do that? Of course I can do that, because x is not equal to x1, x belongs to the open interval containing x1 and x2. So this is x minus x1. Now what do we have? This is true for every x belongs to x1 and x2. Observe, on the right hand side there is no x part, on the left hand side there is an x part. So this should be true for any x, and I know that the derivative of f exists at f is differentiable at x1. So one can of course take a limit x goes to x1, that is what the derivative is, right. So and if I take limit here, there is nothing to take limit, it is a constant thing. So if I take limit on the left hand side, I will get f dash of x1. Don't be confused, we are not writing, we should be writing fx1 minus fx by x1 minus x, but if I put minus on both sides, we will get what we really want. So but this is as good as the other thing, fx1 minus fx by x1 minus x, this is same thing as that. So if I take the corresponding derivative, what we have is this, f dash of x1 is less than or equal to fx2 minus fx1 by x2 minus x1, that is all we have. Now we were trying to compare between f dash x1 and f dash x2, but using the convex nature of f, we only got this. Now how can I get some approximation for f dash of x2, that is what we are trying to see. So that is first thing. Second thing is, so now there are two steps. First step is, here we got for f dash x1, we are looking for f dash x2, it may not be same thing as this, so we might get something. So there are two steps now. First is to look for something to do with f dash x2, then see if that is same thing as this or related to this, that is what we are trying to see. Now observe that there is alternative description for convex function. One can see here x1 was the main point here. So fx less than or equal to this is with reference point being x1. One can do the same thing with reference point being x2. In the sense, I will write x2 here, then I have to change here as x2 minus x, then I have to put some minus here. So these are equivalent. So let me write down that. So further I need to copy this. I don't write again. So the convex nature of the function can be mentioned in the following way. So fx is less than or equal to, in x1 I am replacing with x2, this plus will be changing to minus, then this here it is x2 minus x, not x2 minus x. It's easy exercise to check that this condition is same thing as the previous condition. So previous condition the main point was x1, here the main point is x2, that is the only difference. Now one can do the same result, same computation that we have done before. So this will turn into fx minus f of x2 less than or equal to minus of fx2 minus fx1 by x2 minus x1 times x2 minus x. Again I am just pulling it to the left hand side. So I am writing this as x2 minus x. So there is a slight difference here. Previously it was in the same order, fx minus fx1 by x1 minus x minus x1. Now there is a slight difference. So I need to put some minus here to match it. So if I am putting minus here, I should put minus here also, then the inequality will change. So I am just doing that. So this is I am multiplying both sides by minus. So this is gone. Now this is x minus x2. Again the same idea. On the right hand side there is no x part, on the for the inequality if I am seeing in this way. For this part there is no x part. See, this is x1, this is the x1. For this part there is no x1, there is no x part. Here there is a x. So again one can take the corresponding limit. The limit exists because we know that is equal to f dash of x2. So what we have is f dash of x2 is greater than or equal to fx2 minus fx1 by x2 minus x1. Now it is not a coincidence, but observe that this thing is same thing as this. So what we have is f dash x1 less than or equal to this less than or equal to f dash of x2. So this combines to tell us this is the case. For any two elements x1 and x2, we have this property. So for convex function, asking for non-negativity, non-positivity of derivative is not a good idea, it does not make sense. What makes sense is asking for the increasing or decreasing property of the derivative. If f is convex, can I say anything about the corresponding derivative f dash? Is it increasing or decreasing? Here we have seen it is increasing. Suppose we go back and check, change the starting point to concave, then we will get this greater than equal to, or one can start with this being starting point. Suppose f is differentiable such that f dash is of this property, then it looks like we can just trace this back and say that f is convex function. And the same thing, if f dash x is greater than equal to fx1 for every x1 and x2, then one can trace back and say that f is a concave function. Now similar to the case of in the previous case, what is the problem? We could not say anything about the strict nature of the derivative. Even though f is increasing, f dash can take 0 value, f dash a can take 0, f dash cannot be, we cannot really assure that f dash is non-negative. We can say we could not say f dash is positive, that was the problem. So here we will have the similar thing. So now once we know how to fix that problem, we will be able to fix this problem also. That is all for this session. What we have seen in today's session is the following. We have seen the notion of, we have seen some result that says f is a differentiable function such that f dash a is non-negative for every a, then f is increasing. F dash is non-positive for every a, then f is decreasing. Similarly the other condition also, but we could not say anything about strict increasing, strict decreasing condition, that I left to as an exercise. Now as a next step in the generalization, we are looking for functions that are increasing and decreasing both. The first thing that I can think of is a function that is increasing and decreasing is the convex function or concave function. So further we have seen what is the property of the derivative. We have seen for convex function, if x1 is less than x2, then we have this, that means f dash is an increasing function for convex function. Similarly for a concave function, f dash will be decreasing function. And then as I said that this can trace back to give that f is a concave, convex appropriately depending on what we are starting with. That's all for this session. And yeah, this is where we stop differentiability. In the next session we will do series of real numbers.